We will have assignments, and as I had mentioned, we will be having assignments and quiz for up to 25 marks. So during the class, I mean, I'll give you some written problems which will be normalized to 25 marks, but you might make mistakes there, then those marks are cut. So for that, I'm giving you an option after the class. On some days, I'll ask a few questions and give you about 10 minutes, 10 or 15 minutes. And after that, according to your roll number, I'll ask who has solved the problem. So the first person answers, if he answers it, we'll stop it. He'll get 2.5 marks. And if it doesn't, then we proceed and to the next person, and so on and so forth. And in the next day or for the next question, it starts from the next person. Okay, so you have a option of gaining 25 marks by merely being attentive in the class, because it will be simple questions based on what I teach, and engaging and interesting questions. So if you think and come out with answers, I'll be very happy. And if nobody can answer the question, then I'll go to my PhD students. If they cannot answer the question, then I'll clarify. Okay? So be active, and this will it will not be a one-sided affair, because you will also get an opportunity to speak out. So that is why I planned it like this, because in online lectures, I mean, usually I enjoy teaching when I get response. So that is why we will have it this way. Usually the people who I think the attendance is also weak during online classes, I've noticed. But this will keep you engaged, and you have an opportunity to get the marks. So there's, I mean, like 25 marks you can get simply by this. Okay. So let me start my lecture. First, let me share the slide, right? Where was my PPT? Let's see. Where is it? Where did I take good? Okay. This is the one. Okay. So I'll share my screen. Okay. I have uploaded some of the PPT files of my talk, I think. PPT or PDF, I don't know. Can you see my screen?
Yes, ma'am.
Yes, ma'am.
Okay, so this is lecture 8. And so far we have talked about charged particle drifts in the presence of electric and magnetic fields. We have covered for constant electric and magnetic fields. And so that E is constant in space as well as time. Both E and B are constant in space and time. And we saw that that gives rise to a E cross B drift. We also talked about curvature and grad B drift for spatially varying magnetic field. In this case, grad B was perpendicular to B. Then we talked about concept of magnetic mirrors, which were suitable for confining some kind of particles, where grad B was chosen to be parallel to the magnetic field. And there we introduced the notion of first adiabatic invariant. I've written first twice. And that was nothing but the magnetic moment of the charged particle. So now what are we left with? Let us write down. So the other possibilities are spatially electric field we have not covered so far, and then time varying electric field and the time varying magnetic field. Okay, so let's first consider the case of non-uniform electric field. So I take an electric field of this form. So this electric field, the magnitude of it changes with which coordinate? Yes?
Ma'am, please repeat the question.
The electric field, the magnitude of it changes with respect to what?
X coordinate.
X. And it is also directed along X.
X.
So how would the plot look? For the field lines, it will be, let's say this is the point, then here the arrow can be big. Then if you move here, the arrow can be even bigger. It's changing with X. Then third point, it maybe get smaller. So the vector is directed along X, and it is also varying with respect to X. So we choose a electric field like this. We have also chosen the magnetic field is constant and it is directed along Z, the usual case. So we have, so this we can write as some E, which is a function of X, and it is also X cap, directed along X cap. Or sometimes I can also represent the unit vector as E suffix X, E suffix X, Y, or Z. And the magnetic field is B, which is equal to B naught, which is constant, and it is directed along Z cap. Okay. So what happens if this is the case? We have to understand that. F is the usual Lorentz force, which can be very easily written as Q and then E, and then plus, and then this is the velocity of the particle, cross D, and this will be equal to times dv dt, or the time derivative if we write as mv dot. Okay, v is a vector. So this is the equation. So we can take the components of v. So we will have m, or maybe let me write it like this. Take the m also that side. So this becomes m v x, suffix x means x component, and that's equal to q. Now electric field is directed along x, so we will have E x. Okay, this is the x component of electric field, E suffix x. So this is this, and then we will have, oh, I wrote m also here. Okay, what will be the next term? Plus vy vz, which is v naught. And similarly, the y component will be m vy dot, which is equal to q, but there is no ey, so we will have, this is simply minus vx v0. Okay, now let's say I take the double dot of this. I take one more spatial derivative. Then what happens? This equation, if I take, this will be simply Vy double dot. This will be equal to, I will have Q is constant, V naught is constant, Vx dot. So I'll have to substitute Vx dot from here so that Vy double dot can be expressed entirely in terms of Vy, which is the particle velocity along Y, and all these given electric and magnetic field. So if you do so, you will see that this is like omega c square. Now omega c square has a q square, so it's independent of charge. And then it will have Vy, and then it will have minus omega c by, let's say, B and Q P naught. I'm dividing and multiplying by QB naught to have another omega c, Ex, right? So this gives you you can see that this will be omega, this is omega c, this is also omega c. Again, like charge independent, it has a q here, so this will become charge independent. And this will be omega c square, and then is Ex by B naught. So this is Vy double dot is equal to minus omega c square, and then we will have here Vy plus Ex by B. This Ex is a function of x, or right? We were also representing it just as simple E here. I can write that also. So you have to know that this is a function of x, and the particle oscillates. Even if you forget about this Ex term, particle oscillates around the gyro, along the guiding center x naught x naught y naught, with a certain radius RL in both x negative and x positive. So x minus x naught is basically plus minus RL sine omega t, ct or something like that. And similarly y. So there is a variation of x in the particle trajectory. So it will see different values of the electric field. Similarly, if we take the second derivative of Vx equation, so that we express Vx double dot entirely in terms of uh, Vx, Vy we want to eliminate. So we will take one more derivative and then we will eliminate, so that Vy and Vx equations become decoupled. You can verify that this will turn out to be Vx double dot is equal to minus omega c square, and then there will be a Vx and plus minus omega c. So I'm taking it as a modulus. Omega c doesn't have any sign of the charge. Plus is for ions and minus is for electrons. And then what else? I have taken a derivative, time derivative of this equation. So obviously Vy dot came. But why did Ex dot come? I will write it as Ex dot. Yes.
So it depends on X.
Yes. This means that Ex changes, I mean, as the particle moves, Ex is changing. So for the particle, the electric field is also changing with respect to time. Or you can see it in terms of, let's say you have a function which is a function of x. And then you have to calculate its derivative in time. So this is this. But x itself is a function of time. Let's say x is a function of time. And for the particle trajectory, indeed, x is a function of time. Then how would you express that? This will be, you have to retain this term, which is like f dot, which is basically df by dx, and then dx by dt. So this is like spatial derivative of the function into x dot. So this is how this x dot has been ex dot. We have to retain it in the x equation. So these are my two equations, and I have to solve them to see in which direction is there a drift. So these are my important equations. Okay. Now we know that x minus x0. X0 is, let's say, the guiding center of the particle. So if the particle is gyrating, then this is something like a simple gyration, then it is something like around the same fixed point. This is like sine omega c t. Okay. So we can write x as x naught plus RL sine omega t.
Ma'am,
Yes,
ma'am, the particle is rotating or just oscillating around X now?
it's rotating. But since Ex is a function of x only, I have to be concentrate on x, definitely.
Yes.
Around x, it will appear as if it is oscillating, right? When the particle moves like this, and this is your, this point is like x naught, y naught. Then as the particle goes from here to here, x naught, x component or x minus x0 will appear to be oscillating. Similarly, y minus y0 will appear to be oscillating, right?
Yes,
You can
ma'am.
decompose the equation of this kind of gyro frequency and see to it that they will satisfy this equation. Or maybe we did this also. Okay.
Okay.
So it's oscillating, the x will appear to be oscillating, y will appear to be oscillating as separate independent harmonic oscillators. But the particle is basically rotating.
Okay.
Now, so we have to find the drifts. Okay. So what do we mean? We have if we write Vy double dot, okay, so this is Vy double dot. This will be something like minus omega c square Vy, and then we have to write this as omega c square E naught, right? Because E is E naught cos kx, right? Not by P naught. And then there is a cos, and we have k, and it is x. But for x, I can substitute this. So this becomes x naught plus RL sine omega c t. So this is what we have. Now this is cos something like a plus b. So you can expand it, right? Yeah, any question?
No.
So now we want that we should separate this out. Like if the magnitude of E or it was not slowly varying, I mean those considerations are here that things are slowly varying. So we assume that these are all in a adiabatic approximations. Now supposing we want to basically separate out the gyro oscillation and then find out whether there is a drift or not, and whether there is a drift along X or there is a drift along Y. What should we do? We should at least average it over a cycle, right? So that this average part separates out, and what you are getting back, supposing it is 0, then there is no drift. If you are getting even after averaging, you are getting a finite value of velocity, then that is a drift. So please look at it carefully, the technique, how we find it out. In all the lectures, we are using some techniques. So that is important to understand. So in this Vy, this equation, if we average it over the gyro oscillations and we are expecting a steady drift, then what will happen? Obviously, for a steady drift, after averaging, Vy double dot has to be 0. So average of Vy double dot should be 0. You are expecting a steady drift, so you average over this particular left hand side, which is 0. Average over right hand side is average over this quantity over the gyro period. This is constant, so this will mean average over Vy. And what is varying here? This is varying here. So average over this. So Vy average, which will tell you the drift, can be obtained from this equation, right? So we will have something like, this is your left hand side, which is equal to 0, and the right hand side becomes minus omega c square, and then the average over Vy, which we want to find out. The gyro oscillations, average of that is 0. So that is what we want to find out. And that is equal to omega c square and E naught by B naught, and then average over cos k, then it will be x0, which is, we assume that in one gyro oscillation, the x naught doesn't shift much. That is where the adiabaticity comes into picture. RL sine. So these are all techniques of analysis, but then for a certain approximation. They hold only for a certain approximate case. Okay, so this is what we want to find out. So cos kx, this is like cos kx plus k r l sine omega c t, and we assume that, so we expand, this is like cos a plus cos b. So this will be what? Cos a cos b minus sin a sin b, right? So, oh sorry, this should be x0. So it is cos k x0 cos k r l sin omega c t, and then minus, it will be sin k x0, and this is sin k r l sin omega c t. So this is how I have expanded. Okay. Now we will consider a case where, that's what I have been stressing, that it is valid. Our derivation will be valid only for the case where the Larmor radius is smaller compared to the variations of the electric field. Electric field essentially is varying at a scale length of inverse of k, right? 2 pi by lambda, if this is how the electric field is varying, x component of this, then this is your 1 lambda, and then this is, let's say, e as a function of x, then this portion is 1 lambda, which is nothing but 2 pi by, pi liters. No, it will not write. This is 2 pi by lambda. It doesn't write after that. Yes. So let me open it another file. This was lecture 8. Where did it go? Like 6. What is it? Can't find it. Huh? Let's see. Lecture 7. Where is lecture 8? Files. PowerPoint. Lecture 8. Okay. So can I write here? Draw. Yeah, I can write. So I should kill this. Okay. So what I meant was this lambda will be 2 pi by k. So this, the variation of electric field is at a scale length which is inverse of k. So you have this is E, this is X, and this is varying. Electric field is varying like this, and this distance is lambda, which is equal to 2 pi by k. But I assume that, so in the derivation, if I want to proceed analytically, numerically, as I have been writing codes, you can check it from your MATLAB. That would be accurate. But here, if we are doing some approximations, you can check it, you can write your own code and check it that under this approximation only, this will be valid. So what is the approximation? We will assume that this coefficient, this is anyway sine omega ct term. This will always be equal to or less than 1. So if KRL is less than 1, then this argument of cosine or sine would be less than 1, and then we can expand it. So what is required for this is the approximation that KRL should be much less than 1. It means RL is less than lambda, right? Because K would be 2 pi by lambda. So RL by lambda is much less than 1. In fact, RL by lambda is much less than 1 by 2 pi. So your gyro radius are these small, like this, like this. Particles are gyrating, oscillating only over distance x, which is much, RL is much smaller compared to lambda. So it is under this approximation. Then this is a small argument. And this is basically a small number which will write as epsilon. Okay, so this is small number as epsilon. So cos and sine, when they have small argument, you can expand them by Taylor expansion. And what happens? So let me not take the risk and add new slide. So you know that if you have cos epsilon, where epsilon is very small, the first term is 1. That means cos 0 exactly. But I want to retain the contribution of epsilon. Then it only comes as a square. And that is half epsilon square. If you have sine, then sine epsilon would be sine of a small number. Sine of 0 is 0. But if you have a small correction, then, and the higher terms here would be even smaller because epsilon is much less than 1. So here it will be just, we will retain only up to epsilon square. The other term will be cube here. So, and they are very small, so we will ignore that. And when you do that, what happens is that you can write now this term cos k x naught plus RL sine omega c t. This as Cos kx naught is already there. This is a constant thing. I don't have to do anything. And there will be, this was cos k RL sine omega ct. So I have to substitute for this. So this is 1 minus half epsilon square is k square RL square sine square omega ct. What about this is cos kx naught cos krl sine omega ct. Then there is a term which is minus sine kx naught, and there is the expansion of sine krl omega sine omega ct, but we will retain only up to epsilon. So it will be k RL sine omega ct. Okay, fine. Now if you average this, okay, you average this, average it over a gyro period. So this will be averaged over a gyro period. This is anyway a constant, so it will remain as it is. This average of sine square theta or cos square theta over a period is half, right? But what is the average of sine theta over a period? That's 0. So this term will definitely go to 0. This is 0, and you are left with this term only. And what is that? Is simply cos k x naught, and then it will have 1 minus 1/4 k square r L square. So that's what you get. What did we start with? We started with E naught cos kx. That was the electric field, right? And we were doing, what were we doing? We were doing the averaging of this. So this now we have evaluated. And let's take it this side. So that makes it what does it? You have taken Vy this omega c square cancels. So Vy average will be equal to minus E naught by B naught. And this average we have known, this is cos kx naught multiplied by this factor. So that's like E naught k cos kx naught is simply E. So you get average of Vy is equal to minus E naught by B naught, and then cos k x naught into 1 minus k square RL square by 4, right? Now what is this? This is the electric field that you have applied. So it is basically minus E by B naught. and there is a 1 minus k square RL square by 4. See, so you are having a drift along y when you have a z, b naught along z and e along x. So this part is essentially the same E cross B drift, but there is a correction to it. So this can be written as, so this is your drift, which is in the vector form. I can write it as, so V average. Now I have not evaluated Vx average. I should have done it, and then only I can write it out. But that is what is today's quiz, that you have to show that what is the value of Vx. In fact, Vx average is 0. So you have to show how Vx average is 0. Because what is Vx here? Vx double dot satisfies this equation. So when you average this out, Vx average will come. So why is this term 0? That you have to prove. That is your first quiz question. And I'll give you 10 minutes time for that. So E cross B basically, and V square with a correction of 1 minus K square RL square by 4. You see? So the drift gets modified by this particular factor. So E cross B drift, which was, what was it? It was constant and same for both ions and electrons. But now, if E is spatially varying with a wavelength of KRL much less than 1, then there is this factor which comes in, and that tells you that the magnitude of E cross B drift has reduced a bit. But this reduction will be different for ions and electrons because their Larmor radius can be different. Their masses are different, their velocity could be different, so the Larmor radius, which is V thermal by omega C, will be different. So this, when the electric field is spatially varying, the E cross B drift gets modified and it can generate currents. Okay? Because this drift would be different for electrons and ions. Right? Now I showed you, this is where the concept of Fourier transform will come. But today I will talk only a little bit about it. But I think for your batch, I have covered it in your MSc class. So you should be knowing about it. But I will go through it once more when I introduce waves, etc. But let me ask you one thing. This we got expression when we assume that E was varying, very regular variation. And it had a sinusoidal variation, okay? We assumed it that it had a sinusoidal variation, and then it was given by, and it had a very specific variation with respect to space. Now, this may not be necessary. E can vary in space like anything. You can have something like this. This can be your E versus X. But this tells you that so long that the variations in E are at a scale which are longer than the Larmor radius of the particle. Larmor radius is this much. This variation, even if this is the sharpest in this figure, is longer than that. So long that it holds, you can still use this analysis, and this is the correction you will get. Now, what is this? This is one particular wavelength with which the E is varying. Now, for a function which is like this, very arbitrary, you can always express it as a sum of sinusoidal functions, right? Any function, any oscillatory function can be represented as a sum of sine and cosine series, right? Or a in Fourier transform. So you will have amplitude of E, something like E would be basically sum of E sum over K, and there will be a EK. Instead of E naught, it is E naught K, because it is different for each K. K is sum. And then you will have cos K x 0 plus there will be something like sum over K, and you may always have let's say this was EC, let me call it as ES, where this is the sum of sine series. Okay, so when you do this exercise, this will be basically K square will represent all these Ks. And a more general expression would be that you should have something like, what is minus K square? It's a second derivative of electric field. So this can also be represented, and you would see it more when we do more exercises in Fourier transform. But if some of you are, you can check it for yourself also. Okay, this can be a good home assignment for you. Maybe I should give it to you for writing. Big exercise. So let's insert one slide. And so you can show that in that case, this average Vy, this is equal to average V, and it's only along Y, and this is equal to 1 plus 1/4, and then you will have RL square del square. K was the variation in E. So you should not write del before RL, because RL may also vary. So you should be careful on what operator that goes into. E. So this you can show. Maybe I'll ask it in an assignment how to get this expression. B by V square. Okay. So, sorry, del square. So this tells you the drift when electric field is varying as a function of space. Okay. And this is also known as the finite Larmor radius effect. Drift. This is also known as finite Larmor radius effect on drift. If RL is very small, this term will be negligible. But if RL has a finite value, and so that this term becomes comparable to it, 1, then you will have this effect. This is also known as finite Larmor radius effect. But this term should never exceed this, because if it exceeds it, our approximation breaks down. This expansion has been done only in the small KRL limit. So if you have a condition where KRL is greater than 1, your electric field variations are something are very fast, I mean in space. So then this will not be varied. Let's say your electric field variation is like this and your larval radius is like this. Okay, different colored maybe. And your larval radius is this big. Then this particular expression is not valid. You have to do the problem exactly. And you can do it exactly now. It's a simple linear problem. You can write MATLAB codes and understand it. Okay? Now, so this can give rise to drift, which is different for ions and electrons, as I said. And that's why if you have space varying electric field, then it can produce currents because of the difference between the drift between electron and ion. And it may give rise to certain instabilities. When we read about instability chapter, I'll tell you about one particular instability which is known as the drift wave instability. So we will understand that when it happens. Okay. So now let's take the second. Okay. So first question that I wanted to ask you today is, I'll give you 15 minutes later on, or maybe in between the class. Let me take it like that. Okay. The first question was what? That you had to show that Vx average is 0. Okay, so let me ask these questions. So, new slide. So you have your quiz questions. Quiz questions. And the first question is, how is Vx average equal to 0? This you have to explain it to me, okay? So after 10 minutes or something, I'll ask. The second question is, 2 questions today I'm giving you, and whoever answers it will get 2.5 marks for each question. I'll go roll wise. So you have to say that you want to answer it and attempt it. If you can't answer, it's wrong, then okay, it doesn't matter. If you answer, you get 2.5 marks. And if you don't answer, then, and this way you can accumulate your 25 marks for assignment and quiz. If you don't answer, you have an option. I'll be giving you some written assignments also. You have to submit it carefully. If you make mistakes there, you don't get marks. So ensure that you get at least the upper limit 25. This will help you achieve in that. So first question is, Vx average is 0, you have to show. My second question is, if you had noted, I have taken this, I mean, in the context of magnetic field, I considered two kinds of spatial variations of magnetic field, right? One was when the variation was perpendicular to the magnetic field direction. The other was when the variation is parallel to the magnetic field direction. Here I have today considered variation of electric field along the direction of electric field. What will happen when you choose something like electric field which varies normal to the direction, normal to its direction? Let's say if I have something like E naught cos ky, why didn't I consider that? X cap. Why did I, or maybe this is, you should not try. And what do we expect? Should the calculation be similar or something new? What do you expect? There are simple answers to this question. So right now it is 3-1. So we will, I'll give you, let's say, let's come back at 3:12. We are all online. I'll give you almost 10 minutes, 3:02. So I'm giving you 10 minutes for everyone to think about these two problems and come back to me. Okay, I'm here. So don't go away. I'm here. Okay. So I'll just stop sharing for a while. How do I
Ma'am, should I keep recording?
You can maybe stop for 10 minutes and then start.
Okay, ma'am.
Okay. Have I stopped sharing?
Yes, ma'am.
Okay.